Hi everybody, welcome back to Chem 161. It's that time of the quarter. It is time for Chapter 3. So that's what we're going to be doing forever and ever and ever. Or at least it's going to feel like it anyway. Let's see here. So quiz number 6, that's the Chapter 6 quiz. I number these quizzes by their chapter. That's due tonight. That will close tomorrow so that I can open it on Thursday so you can look at it and see the answers and study for your exam, which is on Friday. Also due this week is lab worksheet number 2. That's due tomorrow. Yeah, so besides the exam, which is now posted, it's not available. You can't actually open it until Friday. Lots to do this week, so make sure you're staying on top of it. And then, take the weekend off. So, I did send out an email about moving exam dates plus or minus 1. If you would like to move your exam to Thursday or Saturday, the default is Friday. If you do not email me, I assume that you want to take it on Friday and will do so. If you email me tonight, tomorrow, Thursday, I can get you in on Saturday if you need me to. Obviously, I can't give you a Thursday day if you email me on Thursday. Once it's Friday, though, it's stuck. And if you email me saying, hey, I really need to take it another day, I penalize your exam by 10%. So make sure you do that before the actual day. Because if it's like 10:30 p.m. on Friday and you're like, hey, can I take the exam tomorrow? I'll be like, yeah, I'm just going to take off points. You could have let me know this earlier, so. All right. We ended lecture last week talking about how horrible Chapter 3 was. And then we talked about what are various properties of light that we can measure. And so the main properties that we were discussing were amplitude, wavelength, and frequency. And I'm an insomniac and have not been getting enough sleep lately, so I apologize. I'm just going to yawn all period. We related the wavelength and the frequency of a photon of light to the speed of light c. And you'll remember that c was 3.00 times 10 to the 8 meters per second. Light is stupid fast. Oh, why am I getting Oh, I'm getting message by students. Hold on, I just need to mute that. Okay. Oh, now I'm dropping frames. Are we reconnected? Is it working? Okay. Sorry, I dropped like 3 seconds worth of connection there. Thanks, Comcast. All right. So, both of those concepts, wavelength / frequency, because those are interconnected, and also amplitude, affect the energy of the light that is incident upon whatever our like surface or our chemical or whatever. And so that gives us two different ways to increase energy. Now, unfortunately, I had to draw my axis this direction because this picture that I had was how it was, and I couldn't flip it horizontally. So as I go down in this diagram, things get more and more energetic. So with the dim light versus the bright light, that's very easy to see. I have clearly more photons in the bright light than I do in the dim light. And you've experienced this probably in the morning after you've woken up. You turn on the light and your eyes go, it's too many photons. Maybe that's not what you're thinking. But like whenever you squint in really bright light, if you have a way to dim the light, it helps because your eyes in the dark, I want to say that it's the pupil. I don't know the parts of the eye. The pupil dilates in the dark to try and accept more light, and then when there's tons of light, it shrinks. But if you have a mismatch there and your pupils are dilated and you turn on a really bright light, it overwhelms your senses and you're just like, it's so bright. And that's because more photons are hitting your retina. They have a higher intensity. They have a higher amplitude. In dim light, there are less photons, and so the effect is less pronounced. So you can think of dim light as being one or two of these small waves, and then bright light would be a bunch of those summed together. Now, in terms of a single photon, or each individual photon, we can increase the energy by increasing the frequency. Frequency is a number of oscillations per second. Now, what takes more energy? Waving your hand like this, where you like wave it 1 time a second, or doing this to it, where you flap it like 10 times a second. And you could do this in front of you, like, I don't know, I'm sort of like waggling my hand like my arm is flimsy. So if I do that once a second, that's easy to do. But if I do it 10 times a second, that's really difficult. It requires more energy. Light is the same way. The more times light oscillates, the more energy it has. All right. So those are our two ways of altering the energy of light. Is we can increase the energy per photon by changing the frequency, or we can just stack more photons together. Now, the reason that I'm mentioning both of these is because it's going to become very relevant later when we talk about the photoelectric effect with Einstein. Einstein made an observation about the photoelectric effect, and the idea of, oh, I can remove electrons by adding enough energy to them is important, but there are multiple ways to add energy to the photons that we're using to remove the electrons. So keep these two ideas in mind. Keep the idea of amplitude in mind because we are going to come back to it, but it is nowhere near as relevant as frequency. Frequency is much more important. Now, what do frequency and wavelength control? It turns out that your eye is sensitive to specific wavelengths of light. The wavelengths that are relevant here are between 400 nanometers and 700 nanometers. 400 nanometers is what your eye senses as purple or violet. 700 nanometers is what your eye detects as red. And then all the other colors that are in between there are a mixture excuse me, of these different not different wavelengths, but different photons of light that peak at a maximum wavelength somewhere between 400 and 700. So, for instance, blue is around 450, where yellow-green is like 525 or so. Your eyes are sensitive to particular colors more so than others. You have a receptor in your cones in your eyes that detects red, green, and blue to different degrees of sensitivity. They cover specific wavelengths, and what your brain does is when it interprets data sent by the cones, oh, I've been hit with this wavelength of light. Your brain goes, oh, you've observed something that's green. And it decodes that for us. Now, how does light function, and how do we interpret this color data? Well, the way that light works is light will strike any surface, such as this innocent, poor working person who's being attacked by this rainbow. And when the rainbow hits you, all of the colors of light are absorbed except for the one that you perceive. For instance, I'm looking at the screen at the woman's shirt, which appears red to me. That's because all of the colors of light were absorbed except for the red, which is either reflected or emitted. And so, since that light has bounced off or from the red object, we interpret the object as red. The color of objects that we interpret is the color of light that the objects themselves give off. Now, why are rainbows hitting people all the time? It's because white light right here, white light is a mixture of every color of light. It's just a random assortment of light. If you pass white light through a prism, what ends up happening is that we diffract the light based on properties of waves. So a prism is another way to show that, oh, light must be wave-like. Because when we bend light through another medium, the colors travel slightly different angles and speeds based on their wavelength. And just that act alone allows us to diffract the light from a beam of white light into a prism. And so you could see the rainbow come through it. All right. Now, again, these are the visible regions that we care about for our eyes, 400 to 700. But that does not mean that our eyes perceive the only wavelengths that are available. Light can be any wavelength it wants to be. If I go below 400 nanometers, we just can't see it. It's invisible. And if we go above 700 nanometers, we can't see that either. Now, you do have options of ways to interact with these things. For example, if we want to interact with things in the IR region, or even the microwave or radio wave region, we can build sensors that do that. For example, interacting with radio waves is very simple. We build an antenna. An antenna will detect radio frequency light. It will then process it and do whatever we want to with it. For instance, we can turn radio waves into information that can then be written or decoded as sound. And so this is the premise by which the radio works. Radio waves are passing through you right now and all the air around you, so that when you are in your car and you turn on NPR, for example, your antenna receives that wave from the station, and then you get music in your car, or you get to hear about how awful the country is right now, because that's what NPR does. It depresses you, right? Here's the public news. Oh, you wish you didn't hear that, didn't you? Yes, I do wish I didn't hear that. But you can't see radio waves. Radio waves are everywhere, but we don't actually see them. An antenna can see them, though. So we have ways of interacting with all these different photons of light. What different types of photons are there? Here's the spectrum of all the different photon wavelengths that we can have. It's called the electromagnetic spectrum. You'll notice that the visible part is this itty-bitty, teeny part of the spectrum. You can also see that there are various things in here that have applications that you're probably familiar with. So we already talked about radio, but we've also mentioned things like the microwave. Your microwave uses light to cook food. Specifically, it uses a frequency that allows water molecules to vibrate resonantly. What that means is that they will vibrate, but they won't have a chance to relax. Every time they absorb a photon, they get excited further. And that causes them to heat up very, 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 very quickly, and then dissipate that heat to all of the molecules surrounding the water molecule as heat. So your microwave cooks by basically causing water to dance a lot. If you're using a wireless sort of hub in your house to connect to a router, or you're using your phone, you're using microwave frequencies that are not the same frequency as the frequency in your microwave. At least I hope not. And the reason I say that is because, so two stories. One is true because it happened to me, and the other may be true because it was a Darwin Award? Is the Darwin Award like when you get something stupid because you died? I want to say it is Charles Darwin. But anyway. Here's the true story about me. I had a phone that had an operating frequency of about 2.5 gigahertz, which is the same frequency as a microwave. And I also had a router that used to operate on that band. And what would end up happening was anytime I used the phone, like I'm talking about like an old phone, like you pick it up on the receiver, not like a smartphone or anything like that. I would pick up that phone to make a phone call, my internet would go out, and the same thing would happen if I tried to use the microwave. Really weird that, why did my internet die? I'm just using the microwave. I'm hungry. I want dinner. And it turns out that my microwave was not completely sealed, which has its own problems. It was old. And those microwaves were interfering with my mobile device's ability to connect to my router because it was all the same frequency. And so my phone was like, what the hell is this information that it's getting? And it's all because it's all in the same part of the electromagnetic spectrum here. So nowadays, I want to say that routers and Wi-Fi are all in the 5 gigahertz region, so it won't interfere with your microwave. Now, if we go further towards the visible region, we hit what's called the infrared region. Infrared is the light that is given off by objects that have a temperature that is warm, I would say. So something warm gives off light in the infrared region. Relatively warm, I'll say. Now, if you heat up something, it will start to glow, and it will give off red light. And the reason that it glows red is because as I heat things, the light that it gives off gets more and more and more, and then guess what color you touch? Well, you touch red, right? So hot objects emit radiation. This is called black body radiation. We're going to talk about that a little bit later. But the first color that you observe from a black body as it heats up is red. And so this is where the term red hot comes from. Now, we don't have something that's yellow hot or blue hot because red is already in the mixture. If I add more colors, what I end up getting is white, right? So the next color that we attribute to a temperature is white hot, which is, oh, it's hotter than red hot. So you've probably heard all these terms before. Night vision goggles can detect infrared light, so they basically sense body heat and then interpret it as green on a screen that you can see. Now, going in the other direction over here is the hazardous stuff. So, beyond purple, we have what's known as ultraviolet. Ultraviolet light is not super good for you because it can cause cancer. The reason it causes cancer is because it will interact with electrons. And it can cause electrons to, like, break a bond, or form a new bond, or create a new compound in, like, say, your skin, and then you end up getting a melanoma because your skin burnt because too many of your bonds broke and new bonds were formed in ways that produce a carcinogenic mutation. And then beyond ultraviolet are X-rays, and then cosmic rays, which are just like the highest power photons that we can get out of there. Now, an interesting consequence of this is that everything on this side of visible light is fairly dangerous, but everything on the other side is completely safe. Unless you're a tinfoil type of person, and you might have heard a long time ago where people used to think, oh, cell phones can cause brain cancer because all of the photons are going through your head. And it turns out that cell phones are incapable of doing ionizing radiation, which is what ultraviolet and X-ray and gamma rays do. They can't knock electrons off of atoms because the photons that are used are too weak. If cell phones could cause cancer in that way, so would your router and your microwave, your remote control from your TV, but you know what else would also do that? Orange. Anything orange would cause cancer. So would green. And don't think blue is out of this. Like, no, that's stupid, right? So, if you hear someone say, yeah, cell phones cause cancer, you have my permission to tell them that they are stupid. Honestly, you have my permission to tell anybody that they're stupid. I'm not going to take responsibility for your actions. So, you have your own agency. Now, I don't know much about 5G. I don't know what frequency it uses. I would assume it's in the terahertz region, but I don't know. Anyway, the point is there's lots of different types of photons out here, and you want to just know generally what each region is and roughly what it can be used for. So, visible is obvious. It's used for seeing. But things like microwave, radio, infrared, X-ray, etc. Generally know the order, like know which ones are higher in energy. That's relevant. All right, let's do some math here. I'm going to give you a blue laser. Blue lasers are actually very dangerous for your eyes because they're very intense. They're also extremely fun. So if you have the opportunity to play with a blue laser, play with a blue laser. All right. What is the frequency of the blue laser? Well, we know that this formula is true. And I want to solve for frequency, right? So I'm going to rearrange my equation. Frequency equals C over lambda. All right. So my speed of light is 3.00 times 10 to the 8 meters per second. And my frequency is 410 nanometers. There we go. But these units aren't going to cancel out, right? So I need to do something like this. So now my meters would cancel out with the meters per second above. So a nanometer is 10 to the minus 9 meters. And then I can cancel this meter with this meter. And I will get something that is in per second. So let's punch all that in the calculator. You're going to notice we're going to get a ginormous number, and that's pretty standard. So 3 times 10 to the 8 divided by 410 times 10 to the minus 9. And we get all the 7s, 3s, 1s, and 0s. 73170, 73170. Over and over and over. There we go, that's what I want. All right, so this photon will oscillate 7.3 times 10 to the 14 times every second. That's absurd, right? How can you count that? Well, someone can. Some device can. I can't. So that would be the frequency. Now, specifically, we're going to probably concern ourselves with the order of the magnitude of the frequency. So something on the order of 10 to the 14 oscillations per second will fall in the visible region. And we can go back and look at that. And we can see that. Oh, they don't list frequencies here. They only list wavelengths. That's too bad. Okay. Depending on which chart that you look at for this, they do have frequencies on there. Unfortunately, this one doesn't. All right. So there's our answer. So for the next problem, let's go back to the microwave. Here's our microwave frequency. 2.450 gigahertz. I want you to tell me the wavelength of a microwave in meters, and I'll give you a hint for your answer. It's called a microwave for a reason. And that reason is, well, you figure it out. I'll check in with you for about 4 minutes or so. So see you in a bit. One more minute, we'll go over the answer. All right, so this time I gave you the frequency, and we need to solve for the wavelength. So we'll just rearrange the equation. And so that's going to be 3 times 10 to the 8 meters per second. Now, this time I gave you the frequency in hertz. Remember that a hertz is 8 per second, right? So this is 2.450 gigahertz, which is the same as me saying 2.45 giga per second, I guess. And then that 1 giga of anything is 10 to the 9 of that, right? Or not negative 9, 10 to the positive 9. There we go. So now our per seconds will cancel out, and we'll be left with something that's in meters. So we've got 3 times 10 to the 8 divided by 2.450 times 10 to the 9. How many sig figs do I get? I get 3. 1, 2, 2. Okay. Now, this microwave is actually way bigger than a micro would be. So this is not 10 to the minus 6 meters at all, right? So I've sort of misled you, but the microwave region in our thing, why isn't this clicking? Is actually, sorry, I'm holding the wrong button. That's why. God, I'm an idiot. Okay. The microwave region is actually over here in the infrared region. So be careful. I have tricked you. No, what the microwave region is, when you look at micro, it's not actually the length of the wavelength. It's just a term that was given to this, but the actual thing that I wanted you to consider, there it is. That's not it. Is the actual device. The microwave oven. How big is a microwave oven? Would you say it's approximately 0.12 meters? I mean, if you have a microwave and you have a ruler, go measure it. Is it roughly 12 centimeters long or tall? And specifically, I want you to consider the place that you put the food into. And what you'll probably notice is that if you go to the microwave, you'll be like, oh yeah, it kind of is like 12 centimeters wide. At least, right? So that means that the wave itself could fit inside the microwave. And it would bounce around some number of frequency times per second if it was doing that, right? So the length of a wave is important for the object that we are manipulating it with, and also for the receptor. All right, so we've played with waves a little bit. I didn't realize there was a second problem here. But I'll let you try this problem too. Sure, why not? All right, so our sun has a peak wavelength around 500 nanometers. And what I want you to do is tell me the frequency of the photon that's at 500 nanometers. But also, I want you to tell me what color 500 nanometers is. Because you might think to yourself, well, I know what color the sun is. But here's the evidence. Let's line this up and see if that empirically matches with your observations. Or maybe you don't know what color the sun is because we live in frickin' Seattle. And it's May and it's still cold. And I hate it. Anyway, tell me what color that is. You'll have to go back a few slides. And we'll go over the answer to this in about 2 or 3 minutes. And then this third problem if you just want to try it. All right, 1 more minute. We'll go over the second problem. Now, this is going to be really, really bizarre because I just learned this. But do you know what knows the color of 500 nanometer light? It's Wolfram Alpha. What does it not know? So, if I scroll down, it tells me this, which actually doesn't look quite right to me. I was expecting it to be more yellow-green. But I guess that's more like 525 or 550 or so. Yeah. So I learned something. I learned that you could just type practically anything in Wolfram Alpha, which is kind of neat, actually. But specifically, the object that I was going for that was this color, I was actually... So I had the wrong color in mind, unfortunately. So the color I actually had in mind, I guess, would have been... Let's just try colors here. No, that's not right. That's closer. That's not right either. So now I'm just wasting everybody's time. That's the color I want. Okay. All right. So this color is very specific to an object that you might be familiar with. This is the color of a tennis ball. Or so. Like, I'm just trying to approximate it. Now, if you look at a tennis ball, you might think to yourself, like, holy crap, that's real bright. Like, my eyes will definitely be able to see that. And the reason for that is that's the color specifically that our eyes are most adapted to see. And that's why tennis balls are that neon yellowish green, is because our eyes are most sensitive to that. And our eyes are most sensitive to that because the peak wavelength of the sun happens to be relatively close to this. And through evolution, we've just selectively chosen for, we want to have eyes that have wavelengths, or that see wavelengths that fall in the region of the sun's maximum wavelength. Now, we'll actually show this on a future slide, which is like right here. Yeah, it's like 3 slides away, so I'll just grab this real quick. Here is the spectra of the sun, of which light is visible and at which frequency. So it's this yellow line in the background. That's the sun. Why don't we make all balls this color for sports? I think specifically for tennis and also golf. This color is used for objects that are small and traveling at high velocities. I think maybe some softballs or baseballs are used for that color, but I don't actually know. Football, I think it's just because the material used, it used to be pigskin. Now it's just whatever polymer or plastic or such that's used. It's just not naturally that color. And then soccer, hell if I know for soccer. I mean, on a soccer pitch, you can see the soccer ball pretty clearly. So I think it's just an issue of, like, for smaller things. A tennis ball is very hard to see because it's whizzing at you at, like, 100 kilometers an hour. People can probably hit the ball much higher, much faster than that. And you have to react very quickly. All right. What is the frequency of this photon? So let's solve that real quick. And then I'll quickly talk about the Earth problem, because we can use light to do this sort of thing, except it's not super practical, because light travels in a straight line. So if we have 500 nanometers for lambda, and there's our equation, then the frequency of our light would be c over lambda. Which would be that divided by 500. And I'm just going to tack this on there. So that cancels those out. And I don't know what this number is, so we'll have to calculate it. So 3 times 10 to the 8 divided by 500 times 10 to the minus 9. So not a number that we would normally write in scientific notation, but your calculator doesn't care. So you know a nanometer is 10 to the minus 9, so just put 10 to the minus 9 in there. And I got 6 times 10 to the 14, so 6.00 per second. So there's our frequency. Remember that if you don't want to write per something, you can always put an inverse unit. So inverse seconds is per second. All right. Now for this light traveling around the Earth problem, if I have, here's my Earth, and my light starts at a point, and I can somehow make it travel along the ground, 7 times per second, I would be able to tell how many times or how far it is per time, right? Because if c equals lambda nu and my frequency is 7 per second, then this should just be the length of each of those oscillations, quote unquote. So c over nu equals lambda should be 3 times 10 to the 8 meters per second divided by 7 times per second. So this is a really stupid frequency because we're going to get a ginormous number for the wavelength. But that's okay. So what's 3 times 10 to the 8 divided by 7? It's 4.3. Well, I guess we only get one sig fig here, so it would be 4 times 10 to the 7 meters. So this would be the path of our light going around the Earth. In other words, this is the circumference. So the radius would then be... So the relationship between circumference and radius is 2 pi r equals the circumference, right? So circumference over 2 pi would be the radius, and we could figure out what the radius of the Earth is. So radius equals that number we just got divided by 2 pi. And so that would be our answer in meters. So it'd be 6.8 times 10 to the 6 meters. Well, I guess this would be 7, huh? Or 7 times 10 to the 3 kilometers. And we can actually look this up and see, okay, what is the radius of the Earth? You know what? I bet Wolfram Alpha knows it. Jesus Christ, it does. So it said 6 times 10 to the 6 meters, and it's more precise than us because we used a very rough estimation. Because I said about 1/7, which is just 1 sig fig. So that's pretty good. And also, that's a fun thing that you can whip out on trivia night, I guess. Light goes around the Earth 7 times per second. I actually had to mention that fact to somebody. We were talking about how people doing high frequency trading would move computers closer to their modem box, and I was like, well, if you're using fiber optic cable, that won't help you because light moves so goddamn fast. But if you have other types of communication media, like electricity, it could help you. Anyway, these are just some applications of light. What we're going to do in the rest of the section, we're going to talk about this for 5 minutes, and we're going to take a break here, is we're going to look at all sorts of other crazy things that light is capable of. So the first thing that light is capable of is if it behaves like a wave, we can get different energy wavelengths and frequencies by playing with it. And so that's going to lead us to this idea here. So if we create a photon that has a start point that is fixed and an end point that's fixed. So say I have a chamber that's mirrored and my photon would just bounce back and forth. I would create what would be known as a standing wave. A model of this would be a length of rope held by 2 people in place that are turning the rope with some frequency. And so this is called a standing wave. Now, you have to apply a certain amount of energy to get the wave to look like a standing wave. If you don't apply any energy, the rope falls slack, right? If you twist it at the correct energy with your partner at the other end twisting it along with you, the rope will go around and around and around, and it'll be like a jump rope, right? Now, I don't know if you've ever done jump rope, probably like as a long time ago as a kid, right? If you don't twist at the same speed or energy as the person on the other side, you just get a mess, and then the rope doesn't go in like a nice repeatable pattern, right? So only certain energies will work to make the rope do certain things. Otherwise, you just get a random mess. And we're actually going to see that in a second here. What I'm going to do is I'm going to load a video of somebody doing a jump rope, and they're going to make the jump rope do this. Where they will be holding it at one end, a student will be holding it at another end, and they're going to try and get it so that this middle part stays stationary. So that it's like they have two jump ropes going at once. And it requires a very specific amount of energy to do this. If you have too much, then you get garbo. And if you have too little, it's rubbish. You don't get to see the wave. The wave starts canceling itself out because it's not the correct frequency. You could, in theory, do this for any number of these gaps in the middle. These gaps that I'm highlighting in green here, these are called nodes. And a node is just a fundamental feature of waves. The node is where there is zero energy, or the sum of the energy is zero. All right. And there's my video. That's what I want to show. So when you are imparting energy into your object, so in this case it's a rope, but like say light or whatever, if you give it the correct amount of energy, you get various types of nodes because you create a standing wave. Now, for however many waves you observe, so this would be one wave right here. Here's two waves. So there's the first one and then the second one. So 1, 2. And then we have 1, 2, 3. And then so on. And I'll just start numbering them out. That's not what I meant to do, but... There you go. Now you'll notice that for the number of waves that there are, which we're going to call n, there are n minus 1 nodes. That's going to be relevant to us later. Because this is just a feature of waves. If you have something that is a wave, it does this. And so when we come back, we're going to see these waves in action in 1 dimension and 2. Because I found a video where they took a frequency plate, you pour sand on it, you could actually see the nodes appear. So we'll do all that when we come back here. But we'll take a break, and I'll see you in 10 minutes. We'll get Mega Man music going again, and I'll see you then. All right, we're back. So let's look at these waves in 1D and 2D. So let me guess, my browser is up to date? Yep. I don't know, I had to sit here and click on this and just open more and more windows until it actually works. Oops, hold on. I want you to pause the videos. Don't. Oh my goodness, YouTube, I hate you. I don't know why YouTube is terrible now. Okay, so let's... So I actually do want his audio because he's going to talk about what he's doing. All right, so this is going to be a standing wave in one dimension.
Your admiring audience.
You couldn't hear him,
and,
sorry.
We will be demonstrating transverse standing waves. I'll also demonstrate traveling transverse waves. Here's a traveling wave. I'm starting the wave by creating a disturbance here with my hand that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down, and you'll see that the little bump in the spring travels from me to Parker and then back to me again. And you'll notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave.
Now, if you've taken physics, you've actually seen this in action before. Here, I'm going to just do that. And you've probably done all sorts of equations with standing waves and so on and so forth. So when they say it's the first harmonic or the first mode, well, Comcast? Okay, I was dropping frames there. When we say that it's the first harmonic or the first mode, what we're going to say in chemistry and quantum mechanics is this is n equals 1. For n equals 2, we're going to try and get 2 standing waves with a node in the middle. And so he's going to try and do that next. And he actually manages to get it for a second.
If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone. And this one, if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me.
Myself. There we go. Let me try and get there we go. So you can see that the node is right here where this whiteboard marker is. And so if I go frame by frame here, you could see that that part of the rope is relatively level. It wasn't there, unfortunately. But relative to the other parts, it's pretty constant. And then he's going to try and do n equals 3 in a second, and I had to pause the video to find that one, but it actually does kind of work too.
No motion going on. 2, 1, 2. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic or second overtone. Yeah,
I keep muting myself so I don't talk over him, but let's see if I can get that back there. So you can see that he's getting rubbish for a second here, but then for a second right here, there's the wave. So you could see it right there. So here's a node right here, and also right here. But if you put too much energy into it, then the wave falls apart, and you can see that it does very quickly. Now we've got nothing. All right, so that was 1D. So we'll close this for now. And as we increase the energy or the frequency, we generate more and more standing waves along with more nodes. Now, that was 1 dimension. Let's look at this in 2 dimensions. Well, I mean, if the video will load. There we go. Okay. I don't know if I have this all captured on here, so... I also think that they copyright strike me on this video last time I showed it, but you know what? Whatever. The reason for it is because it has, this, techno music that plays in the background. So here we go. So these are standing waves in 2 dimensions. The way that this works is they're going to pour this, fluorescent sand onto a frequency plate, and the frequency plate will oscillate at whatever frequency they set it to. And then you get patterns that look like this. Now I'm going to pause the video real quick. What is the sand doing in here? And the answer is, well, if the plate is vibrating, that means that parts of the plate are going up and down really fast, right? But other parts are not moving at all. The nodes are the parts that don't move at all, and so the sand gets shunted towards the nodes. So what you're actually seeing here are where the nodes line up. And you can see down here in the corner, this is the energy or the frequency of the wave that's used. The higher this number, the more nodes show up. Now, at this point, you pretty much get the idea here, and this goes for like 3 more minutes or so. But what we're doing here is we're seeing just a fundamental property of waves, is they make a bunch of nodes. And by picking specific numbers, we can get fancy patterns, and that's cool and all. But the point is that all of this is quantized. What does it mean to be quantized? Something is quantized if you need a specific quantity or amount to get it to do the thing that you are trying to observe. This is the basis of quantum mechanics. Something is not quantum because it's uncertain or because there's a cat that might die in a box or what have you. Quantum mechanics operates on the basis that you need a specific amount of stuff to do a certain thing. And that specific amount is going to be related to energy levels in atoms and how electrons behave. Okay? Now, it does have a lot to do with probability. That's where statistical mechanics comes in. That's Chem 361. We'll deal with that later. But for now, where we're going to start in this discussion that we're going to have for this course is quantum mechanics equals certain amounts of energy are required. Very specific amounts. All right. Now, the nodes that can be produced in multiple dimensions have different types, and they result from different solutions to the mathematical formulas that generate these nodes. For example, you can see that in the top picture, there are nodes that are a certain radius away from the origin. These are called radial nodes. Radial nodes tend to be very low in energy relative to angular nodes, which require a lot more energy. Angular nodes are at some angle about the origin and then just propagate in that direction. So this would be an angular node. You can't see that color, so let me not do that. So radial nodes are a specific radius. Angular nodes are a specific angle going around the origin. The higher the energy, the more nodes you get. Now, over here, you'll notice that I got a lot more radial nodes, or I'm sorry, a lot more angular nodes going around than I did over here, but I have more angular nodes. And so this will be something that we're going to talk about later, is like, what's the energy ordering of all of this? Is there a mathematical way to determine it? And the answer is, yes, we can determine it. It's already been determined. We'll just tell it to you. So you're not going to deal with the 2-dimensional or 3-dimensional integrals that would be necessary to figure out the shapes and densities of these regions that we would carve out for things that behave like waves. Because the whole point of me talking about all of this stuff about light is that electrons behave like waves, and electrons exist in 3D. So we need to understand all the properties of 1D and 2D waves before we can apply them to a 3D wave, which is an electron. All right. So that's where we're going to be going with this later. All right, let's shift gears a little bit. The next topic that we want to talk about for light is sort of a tangential curiosity. This is not a property of light, but more of a property of everything in the universe. An object that is at any temperature will emit frequencies of light from it. Now, the peak of those frequencies will be related to the temperature. I believe it's like 1 over T to the 4, or something like that. But there's a blackbody radiation equation, and what you end up getting is you generate a curve. Let me just show you the curve real quick. There it is right there. That looks sort of like this. And as you increase the temperature... Oops, that's not the pen. As you increase the temperature... Sorry, I'm trying to write slow so it actually looks legible. Because it's doing the weird jaggedy thing here. Like if I do this, yeah. Alright, so if I increase the temperature, the peak will increase in its energy. In other words, its wavelength will decrease. Because remember that shorter wavelength means higher frequency. And so shorter wavelength means higher energy. And so a hotter object will have its peak move in this direction. It'll get more intense because there's more energy. And it will become smaller wavelength because, again, more energy. Now, using this model, we can estimate the temperature of the surface of the sun if this curve models the sun. So the yellow in the background that you can kind of see here. Oops, that's the wrong key. I don't know what I'm doing. There we go. So this yellow line is a measure of sunlight and intensity at specific wavelengths of light measured at the top of the atmosphere. And this curve very closely models this. So what we would conclude is that, well, the formula determines temperature. This is the temperature of the sun, 5,250. All right. Now, if you take all of these colors together, because there are multiple colors being emitted, so you see every color here. If this is the visible region, we have a very high intensity of all colors coming in. And if you split all of those up using a prism, you would get something that looks like this. This is called a continuous spectrum. A continuous spectrum has every color of light in it. And it is just the result of a black body object. Black body radiation emits continuous spectra. So that's cool and all. We can figure out what the temperature of something is. We can look at its black body spectra to see where the peak is, but we would eventually observe every color. Now, an interesting thing that we notice is that, okay, well, if a black body emits a continuous spectra, what happens if we do this with elements? And we actually get a different result with elements. And we'll just actually skip ahead to that real quick here. So if I take a sample that is just a given element, for example, if I put only hydrogen in a cylinder and I try and get a spectra from it by exciting it, what I observe is that I only get very specific frequencies of light. So for hydrogen, I get something at 410, 425 or so, 525, and then 650 or 65, 656. Sorry, and I only observe those 4 colors. So if it's pure hydrogen, you don't get a continuous spectra. You get a line spectrum. So that's kind of strange, right? Like, wouldn't a sample of hydrogen gas be considered a black body? So it should emit every color, but it doesn't? Okay, why might that be? Well, in a homogeneous sample, where everything is just one substance, all in the same phase. There must be some intrinsic property of the substance we're looking at that generates these line spectra. So what is that? Question mark. We're going to come back to it. All right, let's go back to the last weird topic that we're going to talk about. This is called the photoelectric effect. This was an effect discussed and discovered by Einstein. Einstein noticed that if you have light shining on a metal, and the light is a specific energy intensity, you can eject electrons. When I say eject electrons, what I mean is that electrons are detected as shooting off of this metal surface. Now, this is the principle behind solar panels and solar electricity. If light strikes a metal panel, such as a solar panel, the electrons will be ejected. If we can capture the electrons on, say, an electrode, we can then run the electrons through a battery into something that would use the electricity, and then that will go back to the metal to replace the electron that was lost. So we can potentially create a circuit using light to start the circuit. The sun bounces the electron from one side to the other, then the electron goes whee all the way through the battery like it's a slide to get back to where it was. This is the premise behind solar power. Make the sun do all the work. Well, the sun is doing all the work anyway, right? It's already doing fusion and exploding and spitting light in every direction. We might as well exploit that. Now, Einstein investigated this property with a lot of curiosity. If certain amounts of light can do this, what is the property of light that controls this? So he tried... Well, I'm going to cover that up because that's the answer. He did an experiment, and we're going to do the experiment together. No, I don't want to remove the scene. I had the wrong thing clicked. All right, so Einstein observed that if here's my metal, and I send a low amplitude and low frequency photon, he did not observe the photoelectric effect. And so he said, okay, I've seen this happen. I want to do this with higher energy. So what he did was he tried low amplitude but high frequency. And so that would be something like this. And what he observed was that electrons then bounced off. So we have observed the photoelectric effect. And then he said, okay, well, my next idea is to send a high frequency, or high amplitude, but low frequency. So something like this. And what did he observe? No photoelectric effect. And he said, well, wait a second, that's strange. The amount of energy here and here is similar. But it worked in the top example and it did not work in the bottom example. So what's the deal here? And what Einstein postulated was that, okay, in example 1 up here, we'll call this example 2. What he concluded was that for example 1, where I had low amplitude but high frequency, the amplitude is like the number of packets of light. And the high frequency would be the amount of energy each packet has. in example 2 here, we have lots of packets. But we have low frequency. Where no individual packet of light has enough energy to cause the photoelectric effect. And this kind of does check out. Electrons are incredibly small. If I shine light at a sample, very, very, very few of the photons that I shine are going to actually hit electrons. I just am shining so many photons that the chances of me hitting an electron are essentially 100%. But if it's very, very rare that I hit one, relatively speaking, excuse me, it's going to be virtually impossible for me to get two to hit at the same time. So if one photon doesn't have enough energy to produce the photoelectric effect, and I need a second one of the same energy, and it would have to hit at the same time, that's just not going to happen. So that explains what Einstein observed. In case 2, where I have tons of photons, but they each have low energy, there's no photoelectric effect because no single photon has enough energy to cause this to happen. In case 1, I have fewer photons, but all the photons have enough energy to make the photoelectric effect occur. So that's what I observe. I observe electrons being shot off the surface of my metal. So the photoelectric effect is just the launching of electrons, but based on this information, Einstein concluded that this must be true, and he decided to name these photons. Because if light was just a continuous beam of energy, and not individual discrete packets of light, case 2 should have produced the photoelectric effect. You just eventually beam enough energy to get the electron off. But it didn't, so he concluded there were discrete photons. All right. Now, there is a formula that relates energy to frequency. There is a constant that is just used as proportionality. So the energy of a photon is related to the frequency. And we've been saying that all along. You increase the frequency, you increase the energy. And is related to this constant. This is called Planck's constant. And it has this value, 6.626 times 10 to the negative 34, that is not a typo, joules times seconds. So a photon of light has a stupidly small amount of energy. Because we're going to multiply it by a frequency, which is like 10 to the 15. And we're still going to get 10 to the minus 19 joules. Like, it's absurdly small. But when you shoot a mole of photons, which is like 10 to the 23, you get energy that is on the order of things that we can interact with. And that's kind of neat. So our purpose in the rest of this section is going to be playing around with this formula. How much energy does a photon produce? How much energy does a mole of photons produce? Etc. There's Planck's constant. All right. Now, this slide talks about some different terminology that we're going to be using in science for thermodynamics. This is going to be more important for you next quarter in 162, but for now, we're going to just introduce these terms. This box right here that I've highlighted in red and then painted over with green, I'm going to call this the system. The system is just our reference point. So the surface of the metal where my photon is absorbed and my electron is ejected, we're going to call that the system. If I absorb energy energy is going into the system. So the absorption of a photon of light would have this term assigned to it. Endothermic. Energy goes in. Now that energy does something, and the result is that the electron is released or ejected. When the electron is released, it has energy. It takes energy with it, right? If you throw something, you are imparting your energy onto the object you have thrown. It's the same situation with the electron. That energy leaving the system would be exothermic. So endothermic is energy goes in, exothermic is energy comes out. So just terms that we're going to use. Keep those on your back pocket. All right. So let's do an example here. If I use a red laser, like the type that I use to torment my cats, not really torment, they love playing with the laser. I mean, I think they love that. Maybe they hate the laser and they just want to kill it. But I have a red laser on my desk. And let's suppose that its wavelength is 635 nanometers. Let's look at the energy per photon of that. So we know that E equals lambda times nu. Or not lambda, I'm sorry, H times nu. And we also know that the speed of light is just lambda times nu. So what I could do is I could say, okay, well, this is true, right? And then I'll substitute that up in here, which is how we get this expression that you saw on the previous slide that I sort of glossed over. So these forms of the energy equation are going to be helpful based on what information you have. We have wavelength available, so I'm going to write my formula for energy in terms of wavelength. And so we'll just plug in all the numbers now. So we got Planck's constant. Then we got the speed of light. Oh, oops, hold on. I have a mistake. I was looking at this. I was like, this isn't going to cancel out. What did I do? I wrote the wrong units. So this is joules times seconds. Let me fix this before I continue. I was trying to get rid of this in my head. I was like, where did the seconds go? And then I have my wavelength. So this is 635 nanometers, which I'm going to just write like this so that my meters will cancel. All right, what energy is this? Let's find out. So Planck's constant, 6.626 times 10 to the minus 34, times 3 times 10 to the 8, divided by 635 times 10 to the minus 9. And I get 3 sig figs. 3.13 times 10 to the minus 19 joules. So this is the energy of a red photon with wavelength 635 nanometers. In other words, if I hit something with a red photon, I could move it up a distance or potential of this much. It's like saying I have exactly enough strength in my arms to lift a rock 2 meters. Any further than that, and I cannot do it. I don't have enough strength. I will collapse. I'm assuming it's a really big rock, and not that I am, like, completely worthless and have no strength. But your opinion on me may vary, because who knows, right? I don't know what my Dungeons & Dragons strength score is, but if I had to guess, it'd be like 11 or 12, which is above average. I'm a farm boy. I had to lift shit as a kid. It stuck with me. All right, so that's how much energy there is per photon. This is going to be really important to us in the next section. And that number is going to come up again. All right. So I want you to try and answer these questions here. So based on our discussion today, I want you to tell me which color of light, so specifically this is visible light. Oops. So if I ever say what color of light, I am always referring to visible. Because something in the UV region does not have a color associated with it. So I want you to tell me which color of light has the lowest energy and which one has the highest energy. And then I want you to answer this question about the photoelectric effect based on what we just discussed. And then finally, I want you to tell me how much energy is in a laser photon with frequency 4 times 10 to the 14 hertz. So how much energy per photon is that in joules? Go ahead and answer those questions. I'll give you like 5 minutes or so. We'll go over the answers, and then we're going to talk about how the hell do we put all of this crazy shit together that we've talked about today. Because we've talked about a lot of random points that don't really connect to each other, and we're about to find the linchpin. We're going to stick it all together. One more minute, we'll go over the answers. All right, so first things first. So what color of light is the lowest energy? So remember our scale of light goes from red all the way down to violet. And the reason that violet has the highest energy is because it also has the highest frequency. It has the lowest wavelength. Red, on the other hand, is at the other end of this. Red has the highest wavelength. I can't select the color. Oh, come on. There we go. Red has the lowest energy because it also has the lowest frequency. All right. Now for question number 2, it's asking us, here's a frequency, but I don't get the photoelectric effect. If I use multiple lasers, that would be like increasing the amplitude, right? I can use all the lasers I want to, but if my lasers do not have enough energy per photon to make the photoelectric effect occur, it doesn't work. Because the odds of me hitting the same electron with 2 photons at the same time are incredibly tiny. It's hard enough to hit an electron with 1 photon, let alone 2. So this won't work. Should I use a photon with a longer wavelength? Well, this would be, if the wavelength goes up, the energy goes down, so this is no good. But if I use a photon with a shorter wavelength, energy goes up. So this is the correct answer. So you can't use multiple lasers of 4 times 10 to the 14 hertz. No matter how many lasers you have, it just won't work because no single photon in any of those lasers has enough energy to cause the photoelectric effect to occur. All right. Now, how much energy does each photon in the laser have? So let's find that out here. So I'm going to just keep that number there. But if our energy is equal to lambda nu, or not, I keep saying lambda nu, Planck's constant times the frequency, h nu, then that's going to be there's Planck's constant, and then 4.0 times 10 to the 14 per second. And these will cancel. And so I'll get something in joules, which we should because we're looking at energy, right? All right. Make sure you are writing out your units. Quantum mechanics will murder you and leave nothing but a desiccated husk if you don't write your units down, because the formulas get stupid really quickly, and you don't want to handicap yourself by just not having the units handy to cancel out. So I get 2 sig figs. All right. And we're going to notice that there's that times 10 to the minus 19 again, right? A lot of photons that are around the visible region are going to have energy about 10 to the minus 19. And that's just sort of a consequence of the light that we work with. You could have energy be higher or lower. You just pick a higher or lower frequency photon. Like radio is not going to be times 10 to the minus 19. It's going to be a lot lower than that. All right. I have one more thing I want to talk about in the last 5 minutes, and that is how do we put all this together? So we already talked about the line spectrum being weird. Here is the thing that ties all of these aspects of light together. These were all properties of light or observations of light that we had made. And now our job is to try and tie all this to how matter behaves. Because that's the point of chemistry, right? How does matter behave when interacting with other matter? Well, first we need to know what the matter actually is. And that's where the Bohr model comes in. I don't want to bore you with quantum mechanics, but the Bohr model is kind of the most important thing here. So, how do we get this line spectrum to come out of here? We know that pure samples of elements will emit specific wavelengths of light as opposed to continuous spectra. We know that energy can be quantized in waves and that light behaves like a wave. It also behaves like a photon. How are these ideas connected? Somebody, his name was Niels Bohr, said, here's what's going on. We're going to draw a picture of it. Bohr speculated that, okay, I have an atom, and my atom looks kind of like this. Here's the nucleus. And then I have my electrons on the outside, right? But the electrons don't just kind of go wherever they want to. That's not a thing that they do. Instead, my electrons have a structure. And the structure looks like this. Remember these? Electrons have a structure because, and we're going to find this out later on Thursday, electrons behave like waves. Which means that they have some amount of energy. They have quantized amounts of energy. They settle into these regions, n equals 1, n equals 2, n equals 3. So my electrons are going to be like this. Now what happens is when I send light in, so here comes my light. So there's my light, and my light has a certain amount of energy. This light will take this electron and go up, and now it's up here. Then what will happen is my electron will eventually fall back down, and in doing so, it releases its own photon of light. The photon that's released, it's what you see. And so what he speculated, he being Niels Bohr, was that, okay, if all of these topics are interconnected, I can only absorb certain frequencies of light in my atom. And that energy amount is going to be related to where my electron is coming from and where it is going to. So this would be some energy for this transition. This would be some energy for this transition. And only photons that have that energy work. Now, if I have more energy than that, then what my electron would do is it would go, ooh, and it would land back down here. So slightly more energy is fine, but the only photons that come out would be this difference right here. So we would only observe this photon of light and this photon of light. Or maybe if this happened, we could observe this one. I realize all these numbers should be reversed for if I have an electron falling. But Bohr said, okay, these are the only possible energies that are allowed. These are the only quantities for this atom. And so this is where the Bohr model comes in. Electrons live at specific energy potentials, which we have ascribed to a wave. We called those n. Electrons can bounce up and down based on the energy that they absorb, and they'll go up to a higher n. And then when they're done, when they want to go back home, they release that energy that they had absorbed. And we see that as light. So this is all of those experiments that we talked about today and very briefly last week on Thursday all lead to this. Electrons have structure around a nucleus. They are not just randomly traveling around. They are actually in a very specific pattern in how they arrange themselves. Now, they still have a trajectory, but what they are behaving like is three-dimensional waves. And if that sounds interesting and neat, join us on Thursday, where it gets even more fucking crazy. That's really all I have for that. So, make sure to get quiz number 6 in tonight. It closes tomorrow. Lab worksheet number 2 is due tomorrow. It closes Thursday. The exam is Friday. If you need me to move your exam, send me an email. Please don't use Discord. I need your name and section number. Happy to do it. You can put your exam on Thursday or Saturday. That's it. See you on Thursday. Take care.